Good morning, everybody. My name is Giulio Poggiaroni from EUBIA, European Biomass Industry Association. I will moderate this webinar together with my colleague James Ling from Greenovate Europe. And together we will talk today about cogeneration from biomass in the EU. We are going to do so by presenting you, by giving you 4 presentations. The first is going to be an introduction from COGEN Europe on the status of cogeneration from biomass in the EU. Then you will go through the experiences of 2 projects funded by Horizon 2020, Blades and SmartCHP. And then at last we will have, I will introduce you to BioCOGEN 2030, which is the stakeholder platform born out of the cooperation between the project Blaze and the project SmartCHP. And more on that later. So I will give the floor now for a for some quick words to my colleague James, who will introduce you to the technicalities of the webinar, and then I will move on to present the first speaker.
Thanks, Giulio. So welcome everybody. Thank you very much for joining. If you could just change the slide, Giulio, thanks. So we're recording the webinar. It will be put online. Also, you'll receive the slides as well. You're in listen only mode, but we would very much welcome your questions to the speakers. So the idea is that you can enter your questions at any time in the question box or control panel. If it's directed at a certain speaker, maybe also include their name just so we can make sure it's addressed to the right person. So at the end of each presentation, I will address 1 question to the speaker, and then whatever questions we have left, we will try and address during the discussion session at the end of the webinar. So keep your questions coming. We'll try and answer as many as possible. And that's all, I think. If you have any technical problems or questions, I'll be moderating the chat, so just type them in there. Giulio, back to you.
Thank you, James. So I will introduce the first speaker in the first presentation. We're going to have Hans Korteweg from COGEN Europe, Managing Director at COGEN Europe, who will give us a great overview on the status of cogeneration in Europe. So Hans, the floor is yours.
Thank you. Just bear with me 1 moment. I will bring up my slides. Oops, wrong presentation. Hopefully you can see.
Yes, we can see the presentation.
Yes, apologies for that. There's always a technical glitch and it seems to always fall on my hands. So good morning, everyone. Thank you for the very kind invitation to present COGEN Europe and the status of cogeneration in Europe, and more specifically the role of biomass in cogeneration in Europe. So just very briefly about our organization, it's quite straightforward. We're the cross-sectoral voice of the cogeneration industry in Europe, and our primary focus is the advocacy, working with EU institutions, the European Commission, the Parliament, the Council and Member States, and we do so working with our members to build robust arguments using their expertise, and of course working with many different organizations, as for instance demonstrated this morning in today's webinar. Our membership is quite diverse. We're a hybrid organization in the sense that we represent both national associations, so 12 different national associations from across Europe, but we also have around 50 different corporate members. And I think this is unique about COGEN Europe, is that we represent the entire value chain for cogeneration in Europe, starting from the manufacturers, the OEMs, so from kilowatt to megawatt in terms of the manufacturers, but we also represent the utilities, the ESCOs, and finally, of course, we also represent the end users, those who actually use the technology. So now I'll pivot in and discuss the benefits and where we see cogeneration going in Europe from the medium to the long term, but also, not forgetting about where we are today as part of that journey. But before going there, just some very simple information about cogeneration. It's a beautiful technology. The concept is very simple. You have a single input and you have two outputs. So you simultaneously produce heat and electricity at the same time. And that allows you to transform up to 90, even 95% of the energy into useful heat and electricity. Another beautiful concept about cogeneration is that it uses all energy sources today and the future. Today, and you'll see this in my slides further on, we use natural gas, we use heat, we use different forms of technology, energy sources. So there's no real limit in terms of what is used, but we can give you a projection of where we are today and how that will look like in the future as well. So some very basic facts, the benefits of cogeneration in terms of efficiency. It transfers more than 80% of the energy to usable heat. And this can be used in factories, buildings, homes, you name it, as opposed to having to produce your heat and electricity separately. Cogeneration is all about putting energy consumers at the center. That means industry. Over 90 million European households in Europe benefit from district heating. There are over 100,000 active energy consumers in Europe. That means, individual dwellings, homes, but SMEs that use CHP to generate their own heat and electricity. You also have many iconic buildings. You may or may not know this. For example, the headquarters of the European Commission uses CHP. Some of the European Parliament buildings use CHP. Iconic Buckingham Palace uses CHP, and the list goes on. So today we see cogeneration responding to many new challenges, such as cutting emissions, lowering costs, saving energy obviously is key, but because of the decentralized nature and the range of different sizes of the technology, it helps empower citizens, but also businesses, large businesses, industry. The technology provides flexibility today already. In the future, that'll be even more so important. Because of its decentralized nature, it avoids costly grid reinforcements where you have more centralized baseload power. It's already smart grid ready. And then finally, of course, it helps integrate renewable energy at lower costs. So this is an overview of where we see, where we have cogeneration today and where it could be in 2030, and then the aspirations of the industry in terms of the technology in the industry in 2050. So today, cogeneration represents around 11% of the electricity generation in Europe and about 15–16% of the heat in Europe. However, it does contribute up to 21% of the EU CO2 reduction target and 14% of the EU's energy efficiency target. And this is the 2020 targets I'm talking about. And already renewable cogeneration has doubled in the past 10 years, if not tripled, in fact. So going from 13% 10 years ago to approximately 30–33% today. Looking forward to 2030, obviously a topic of discussion today in Europe, in Brussels in particular, with the European Green Deal and the previous clean energy package. We have, through various studies, EU co-sponsored studies, extrapolated that with the right policies in place, there is already the technical and economic potential to double the role of CHP in terms of generating electricity in Europe and increasing the heat output from, say, 15% to 25%. And again, these are key contributors of the existing EU's 2030 environment and energy objectives, so contributing up to 23% of the EU CO2 reduction target and about 15% of the EU energy efficiency target. And then looking to 2050, we see and we are hoping to see the technology to at least double in capacity in terms of cogeneration and the energy mix, but also we'd like to see cogeneration prioritized for thermally generated electricity and heat, so we can avoid wasting valuable energy in 2050. So now a little bit about cogeneration in Europe. Some of these things are redundant in terms of what I showed you in terms of the pathway, but you can see that over the many years since 2012, CHP has been a consistent and reliable producer of electricity, hovering around 11% in Europe, and also the heat share hovering around about 15% in Europe over the last 8 to 10 years. In 2017, CHP represented 122 gigawatts of installed capacity. In terms of translating that into CO2 reductions, it helps reduce up to 280 million tons of CO2 and 630 terawatt of primary energy savings, which is equivalent to approximately 60 million cars running on our roads today for a year. Here's just an overview of generation by country. Obviously, every country is different. They have different policies in place. They have different geographical weather conditions and so forth and so forth. But you can see countries like Germany, where CHP is the largest in the market, but not in terms of the overall mix. Italy is a key country in terms of CHP, as well as the Netherlands, Spain, and many different countries across Europe. You see the share and also the in relation to the mix in these different countries. So I discussed a little bit about the fuel mix. It has been predominantly fossil. In the past, lignite and coal had a much more significant role, but if you can see the trends here, that has been replaced largely actually by renewables and natural gas. So as I mentioned before, the share of renewable CHP has gone from 13% to almost 33% in the last 10 years. A majority of that is in fact biomass, but there is a growing share in terms of waste heat and biogas. What is clear is that at least in the past, and I guess in the short term at least, natural gas will continue to have a role. But as we are discussing now today in Brussels and across Europe, is the role of the decarbonization of the gas grid. So there we talk about the different types of hydrogen, synthetic gases, and so forth, which all can be used with CHP from the smallest unit to the largest unit. But what we see here is a steady decrease of the use of fossil fuels, and of course that trend will continue as we get to 2030, and obviously by 2050 being carbon neutral. And this is in fact my last slide. Is an overview of market develops in Europe in the last say 5 years, between 2013 and 2017, and you have interesting trends. What's clear is that renewable and natural gas cogeneration continue to play a significant role in terms of the installed capacity, and there is growth in the commercial and domestic cogeneration over these past 5 years. This is part of our national snapshot survey that we conduct with our members and partners every year. And one of the questions we put to them obviously is the short-term prospect for cogeneration, so the 5-year outlook for CHP markets in Europe, and about 75% of those responders say they expect steady or moderate growth in the next 5 years for CHP. The segments that are expected to really grow are the industrial side, but a small commercial using both natural gas and also renewable sources. So in fact, that's the end of my presentation.
Thank you so much, Hans. That was really interesting. We're just going to take a couple of questions. The first one was related to your previous slide, I think, or the slide with the map. Maybe you could just go back to that. Asking about the purple countries on the map.
This one.
Yeah.
So those are, in fact, red. So in these countries, you see, I can barely see the slide as well, but you see installed capacity declining. So that would be Spain, Portugal, Greece, the Netherlands in terms of installed capacity. But in some cases, despite the installed capacity, so closing of facilities, other facilities have actually been managed to increase the total generated electricity. So you have some wins and losses there.
Okay, thank you very much. And specifically on bioenergy or bio-based CHP, what do you see as the outlook there in the coming years?
Well, as I mentioned before, about a third of the fuel for CHP is coming from biomass. That's the largest contributor, and you see a lot of that obviously in district heating, especially in the Nordic countries. And I think we will at least maintain that level, if not grow. But then there's obviously a lot of potential for biogas and other renewable sources. But biomass obviously plays an important role in terms of already a third of the CHP fueling, up to right now 11% of the electricity generated in Europe and 16% of the heat. So it's a significant contributor in that respect, and also contributing towards the different EU energy and environment objectives that I showed as well. So despite the fact that it's only 11% electricity and 16% of the heat, a third of that is actually coming from biofuel and contributing towards those different targets. So a key player, certainly.
Very good. Okay, we're going to move on then, but you're going to stick around, Hans, also for the discussion. So
yeah. So
if people have more questions for Hans, then please keep putting them in the question box, and we will come back to them.
Great.
So I would invite Giulio to introduce our next speaker. Thanks very much, Hans.
My pleasure. Thank you, James.
Thank you so much, Hans, for your very detailed presentation. So now we move on into the project section of our webinar today. We will start with the first project, the Blades project, and it's as I mentioned at the beginning, today we're going to have two projects dealing with cogeneration from biomass using different technologies, but still in this field. And I will give the floor to Professor Enrico Bocci from the University Guglielmo Marconi in Rome, which is the project coordinator for the Blades project. Enrico, the floor is yours.
Sorry, okay, I have to activate okay, now you see me? Okay. Okay, and I hope that you see also the screen. Okay. You see the screen?
Yes, we see the screen.
Okay. So, okay, Blaze, you see, is a biomass low-cost, advanced zero-emission, small to medium-scale integrated gasifier, fuel cell, combined heat and power plant. So it's really in the stream of what you you listen at the last presentation. Okay, because it's a project. Okay, when you take you try to take more waste heat, so there is a problem of using a different biomass, no, in a different in the same reactor for a different period of time, in order to use more type of biomass, so also biomass that are not available for cogeneration. And in this case, we try to use a bubbling bed gasifier. So, okay, we have to crush the biomass in little pieces, but we can use also high humidity biomass, and also biomass with, for example, localistic value. Also biomass with high ashes, high content of contaminant and so on, because we have also sorbents and catalysts inside the gasifier, the reactor. So, and we use the hot gas conditioning in order not to waste heat and not to waste energy, in order to cool the gas and have the cold gas conditioning. And after we use a solid oxide fuel cell, so a fuel cell, in order to increase the electricity and so have almost zero emission at the end. So this means that this project is aimed to increase biomass, okay, reduce the increase the efficiency of this power plant, reduce the emission, and so it is exactly in line with the trend in order to increase the cogeneration, increase the renewable energy in cogeneration, decrease the emission, and increase the efficiency. Okay, in particular, okay, we try to do that before with a very large work on the lab scale that is already started, because in more than 1 year this project. So we already make a lot of biomass analysis, a lot of analysis also of the ashes, of the melting point of different biomass waste and contaminants. So a very detailed analysis of biomass and gasification and conditioning test. The gasification and conditioning tests still are running. We already started, but still running. We have a lot of tests on bottom cell tests, a little bit soft for contaminants. And we are also starting the stack soft test. After we realize the 100 kilowatt more or less gasifier biomass input with 25 kilowatt soft. Okay, this meaning that normally the power will be 50 kilowatt of thermal input biomass for 25 kilowatt of electric power. Okay, reaching an electric efficiency of 50%. The experts doubling the efficiency, more than doubling the efficiency of the actual biomass to electricity power plant. After there is also modeling and design for this activity, and so there is also the assessment part and estimation production part. So in this project we try to develop a low cost plant, and we arrive to a breakthrough in cost reduction, performance increase. So reduction of emission and increase of possibility to put more biomass waste. So I will a little bit I will show you some photo about the different work package. Okay, so the biomass assessment already started. This is the facility of Enea Trisaia in the south of Italy. Here there is the facility also in Aquila. So there are all on bench scale reactor, bench scale reactor, in order to test biomass classification and hot gas conditioning. Okay, this is the soft bottom fuel cell test in Enea Trisaia, so near Casaccio, near Roma, and this is the TFL in Switzerland. Okay, the stack test. Okay, this is the work package 3. The work package 3, so there is also all these other unit of classification in University of Teramo and University of Aquila. Okay, this is for the online autonomous test of many hours for the conditioning system. It is mainly composed of ceramic candle filters inside the feedboard of the gasifier, and there is also sorbent in order to eliminate the contaminants. And this is the stack soft test that you already see in the other slide. Okay, so the work package 4 modeling is already also started. We start CFD modeling of the reactor, and we have also made all the Aspen simulation in all the plant. Okay, in order to understand and better make all the integration of the plant. Okay, of course about that there is a very different system that we are analyzing. Okay, more than 23 combination of what the plant can be, also changing some temperature and so on. Okay, this is the stack of 25 kilowatt that is made by solid power. Okay, that will be integrated with the gasifier. This is the gasifier. Okay, this is already built. Okay, so it's an electric heated gasifier. This is meaning that I put biomass here. Okay, the biomass is heated by the char that is unreacted char that go to the combustor. Okay, there are two bubbles in the bed, but there are different differentiation velocity. So this meaning that there is a recirculation of material, hot material, from the combustor to the gasifier, in order to give the heat needed for the reaction of the gasification. So I have a syngas that is free of nitrogen. It's high calorific value syngas. Okay, it's only mainly composed of hydrogen, CO2, and a little part of CH4. Okay, and so it's a very good gas in order to send to the soft. Of course, must be there is a filter candle in order to eliminate the particulate, and also there is an elimination of sulfur, chlorine compound, and so on, contaminants for the soft. For the techno-economic, social, environmental assessment, okay, also this is already started. We have made a preliminary economic evaluation, also social aspect, legislation, environment, and health and safety evaluation. Also the work package dissemination registration results is already started. Okay, we launched the website. We launched, okay, in our website there is still now there is a good deliverable about the biomass analysis and about the hot gas conditioning, especially for the soft. So a list of all the literature, contaminants, and so on. And for the biomass, also the experimental results. For the soft, still we are in the next 3-4 months we will finish this part, and we put also the deliver about the experimental results about the conditioning and the solid cycle itself. So this is almost on. Okay, so I go very fast, but I think that maybe you can ask me anything about this project. I would like only to show, okay, that this plant, okay, have to reach more or less 50% of efficiency. That is, a biomass plant normally is in range of 10-20% of electricity efficiency, and so we will double, okay, using the hot gas conditioning and the solid cycle cell, the efficiency of the plant. We will also reduce the cost, because, okay, the solid cycle cell is a part that's very high cost, but regardless, because it produces more than double the electricity, it will be reduced also the cost. And also regarding the overall efficiency, it will be very high, okay, because we will work at high temperature. We will have heat at high temperature available. Okay, so a very high quality heat for any kind of purpose. This is almost the project. Of course, the main problem here in this project is to make functioning all that, because all the contaminants, all the different biomass, and so on. So it's very interesting things in order to work, also in order to try to make functioning all the system, and have at the end of the in the next 1 year and a half the plant that's functioning. Okay, this is more or less okay. So I hope that this is all. If you have any question, please ask me. Okay.
Thank you very much, Enrico. That was very interesting and very complete. I'm just going to ask you one question now. We have a couple of questions related to how you are cleaning the syngas for the SOFC,
Yes.
because you should need very clean gas.
Yes. This is a very important question. So it's very important if there is a primary hot gas conditioning. So there is some solvents here. Okay, so you mean that you use calcinated dolomite, okay, with a little bit of oleoline, because otherwise we have too much ashes. Okay, so yes, we have the ceramic candle, but otherwise the cake in the ceramic candle will be always full. Okay, so you have to put the nitrogen back full in order to clean too much often. Okay, so we put some primary solvents here in order in the bed. So there is not only sand, but there is calcinate, dolomite, and olivine, and this will increase a little bit the syngas production, decreasing the tar. Okay, and also some decrease a little bit. It's interesting. Our experimental data, there is also a very decrease of chlorine and sulfur compounds. And this is the first primary condition inside the gasifier. So we have to make first a primary condition inside the reactor. After, there is the ceramic candle filters. This meaning that these are ceramic, okay, at temperature. This meaning that there is no way that particles can go outside here in the gas. And after, you have a final at temperature sorbent reactor. Okay, if there is a sorbent, as kaolin and other things, for chlorine and sulfur compounds. And so in this way, you allow that there is no particle because there is the filter here, okay? The reduction of sulfur, chlorine, and tar is also in primary here. And here after there is, okay, I forgot to tell you also there is nickel-based catalyst for tar, okay, in order to reduce also the tar. And after there is the less temperature, low temperature, because these are almost at the temperature of the gasification. The steel reforming of tar is a temperature reaction. And after there is the secondary hot gas conditioning at a lower temperature in order to decrease also the last, in order to have, the goal is to reach less than 1 ppm of sulfur, chlorine compound and so on. And very low tar, especially we destroy here also the heavy tar and also here the heavy tar. So this means that the two rings, the one rings, they will be almost all converted. This will remain a little bit part of methanol, benzene, but this is good for the SOx, okay? So there is no problem, okay? For carbon deposition, other things here inside the SOx. I can go deeply in the detail of that, but maybe it's not needed. Okay, it's not what he want to answer the question. Okay, so I think that it's very complicated here, the hot gas condition. This is the part that it's very more important in order to be successful. Okay, this is very dependent on the very different type of biomass. Okay, so this means that especially if you have organic solid multi-solid waste, okay, that's very same, very ashes, very different material and so on. This is can be you can have a very problem here. Okay, so okay, okay, I will stop. Okay, maybe too much answer for one question. Okay, sorry.
No, that's fine. Thank you very much. That was very complete. But yeah, we will move on now. But you will also stay for the discussion at the end. So we have some more questions, and we will try and address them then. So thank you very much, Enrico. I would invite Giulio to present our next speaker. Thank you.
Thank you, Enrico, for the presentation. So now I'll give the floor to Bert van der Beld, which is CTO at Biomass Technology Group, which is the project coordinator for the project SmartCHP. Bert, the floor is yours.
I don't see the screen yet. But... okay.
We see your presentation.
Oh.
Okay.
Okay.
Yeah.
So, yeah, thanks for this introduction. And for me, it's a great pleasure to present this SmartCHP project today. So in the next slides, I will give a little bit of further explanation on this concept and also on the background of this project. SmartCHP, it's also a European research project. We aim to develop a novel, new, flexible cogeneration unit. Basically, the whole system is based on the use of fast pyrolysis oil in a modified diesel engine. The pyrolysis oil will be produced from renewable lignocellulosic biomass. And I think this project can further support the use of renewables for the production of electricity and heat. And of course, as mentioned before, we have the European Green Deal, and I think the system can also support that. The market is huge, and with this SmartCHP, we expect to be able to have an 85 to 95 reduction in greenhouse gas emission, which is quite high. But furthermore, also when you install these units, it will bring new jobs. It will create or bring new economic activity, in particular in rural areas. It's possible to get more renewables and help to mitigate these climate changes. So what is SmartCHP? Well, it is depicted here. We start with non-food, sustainable biomass, non-food biomass that will be used. And we think about, for instance, agricultural residues, forestry residues, organic waste, etc., and so on. And that's sent to a pyrolysis plant. And before further going into this SmartCHP concept, I would like to spend a few words on fast pyrolysis. Maybe it's known to you, but fast pyrolysis is a thermal cracking depolymerization of organic material in the absence of oxygen. We are mainly aiming, and the main product is liquid bio-oil, the FPBO. Besides that, we get some gas and char. It's used within the process. Minerals are recovered at low temperature. And if you look at the current status of this technology, the technology is maturing. Commercial plants are available or under construction. There are plants in Netherlands, Finland. There is one under construction in Sweden, another one in Finland. And if I look at the total production, I would estimate that early next year, the European production capacity will exceed 100 million liters annually. So the product is there. But what about the properties of this so-called oil? That's shown here. For sure, fast pyrolysis oil, it is a liquid. It's also a fuel, but also for sure it's not an oil. And that's illustrated in this table on this slide. For instance, if you look at water content, we have 25% water in the oil or in the pyrolysis oil. Normally a fossil fuel, it's virtually free of water. The density is 1.2, whereas diesel has a much lower density. The heating value of 16 compared to 42 for fossil. It's acidic, pH below 3. The viscosity is a little bit higher. And I also mentioned the cetane number because we are looking at using this oil in a diesel engine. The cetane number is an indication on the ignition properties of the fuel. Normally a diesel, it's maybe 45 to 55, somewhere in that range. Well, we think we can even not reach 20. In certain cases, it's mentioned it's below 0, but it's very low, so it's difficult to ignite. So if you look at pyrolysis oil, it is available nowadays, it is sustainable, but if you want to use it in a standard diesel engine, it's really a challenge. And that brings me back to the concept that we want to develop. This fast pyrolysis oil, we use it as a fuel for the engine. So we will further develop the engine. The big advantage of a diesel engine is that the electrical efficiency is quite high. You can have efficiencies above 40%. In addition to that, we have a combustor boiler, and we use the flue gas from the engine. In particular, it's helpful at if we run the engine at low loads, we can add additional fast pyrolysis oil to the boiler, generating additional heat. And that's one way that we can have a high ratios, or we can change the ratio between heat and power over a wide range. We also know that the emissions are too high, so we will also develop the flue gas emission treatment, that we have low emissions from the system, high flexibility on the output, heat and power. To find the optimal conditions, we are working on a model for the system, but also to develop a smart control unit. So we will be able to, depending on the demand, to find the optimal operation window. Well, this fuel, we have the heat and electricity. We can look at different markets, well, you can look at small scale industry, the service sector, like hotels or hospitals, public buildings and so on, islands, remote areas. It might even support district heating. The size we are looking at is typically 100 kilowatts up to 1 megawatt. That's the size we have in mind for a commercial unit. So it's what we call small scale. We have some specific benefits, or we think we have specific benefits, because we are running on fast pyrolysis oil. It's a way fast pyrolysis oil can deal with a lot of different types of biomass and also residues, converted into a more homogeneous liquid, and using this liquid to produce the heat and power. I don't think I have to explain more on the efficiency. I think it was already well done in the first presentation by Hans on the advantages of combined heat power in general. If you look at the more renewables, it is flexible. I think it can be if you look at the European Green Deal, we aim for energy neutrality, at least in 2050, and also with increasing the variable renewables and the fluctuating renewables like sun and wind, we also need more renewable backup power, and I think SmartCHP can contribute to that. Well, less greenhouse gas emissions, I think it's clear, and we can have a very high greenhouse gas emission reduction compared to fossil fuels. So I think the benefits are clear. Then, of course, the question is how will we achieve, or what will we do to achieve these goals? Well, I try to summarize all the project activities on this scheme. At the end of this project, we aim to have a validated design of a full-scale smart CHP system, and we decided that it will be based now on a 250 kilowatt electrical system, and it will also include a business plan or exploitation plan. Well, to have this validated design, we need a prototype, and within the project we will develop and construct and test a complete 50 kilowatt smart CHP prototype. So it will include the engine, it will include the combustion, it will include the flue gas treatment and the smart control. And to be able to do that, we need a number of technical activities, which are the blue parts on top of this scheme. We will do some fundamental, more basic research on the process of combustion, because they are quite different from fossil fuels. We need the engine component development and engine testing. We will further develop the burner and the boiler, and in particular the burner needs specific attention, but also the conditions are strange. And we are using the flue gas, so low oxygen content or changing temperatures and so on. For sure, we need emission reduction, so there will be a kind of a denox or further convert CO or remove particles and so on. That will be designed and tested also in the project. We will do the system modeling, and that should lead to a smart control system, a real smart control system that will also be implemented on the prototype. Of course, it's not only technical development, we need also supporting activities to be able to make an exploitation plan or to make a business plan. We will do work on the biomass availability and the selection, and a number of selected biomasses will also be converted into pyrolysis and tested in the different units. There will be a combined heat power market assessment. There will be some specific case studies for implementing a smart CHP system at different regions in Europe. Of course, a techno-economic assessment. We also need some additional work also on sustainability and a life cycle analysis, socio-economic aspects, and it seems to become more and more important also to look at the public perception or acceptance of biomass. Specific policy, regulation, legislation, which is also different in different European countries. So we need a good overview of that, and all it will feed into our final aim, this full-scale smart CHP system, at least the design. And who will do this work? One more slide. We have 10 partners from 6 countries in Europe. The project duration is 4 years, and we just completed the first year of the projects, and the total grant is about 4 million euro. Below you see the partners in this project, and BGG, we are the coordinator of this project. We will also work on the engine, and we will host the smart CHP prototype. And besides that, our consultancy group will also work on the sustainability issues for this project. Abate Motoren is also from the Netherlands. They do the engine work and also develop the smart control system. Kaakpax from Belgium is doing the biomass selection and also providing the biomass. Dowell is a French company. They will do the techno-economic assessments, and also the exploitation plan is their responsibility. DTU from Denmark, they are working on the modeling and preparing the overall system model required as input to the smart control system. Greenovate from Brussels on the dissemination and communication. Exergia from Greece is working on the CHP market to get an overview of the CHP market, but they will also work on the socio-economic aspects of this concept. OE from Germany is specialized in the burner boiler work required in this project. TEAG is also from Germany, specialist on flue gas treatment. And we have the University of Eindhoven, who will do some basic research and also some engine work on the combustion of fast pyrolysis oil. And well, it's a very complementary and active group, and well, we are confident, and we hope that it will lead to a successful development of this smart CHP concept. And that brings me also to the end of this presentation. So thank you for your attention.
Thank you so much, Bert. Very good. Just have time for one question. I don't know if you want to pop your webcam on for a minute, just so people can put a face to the name. And yeah, we have a few questions. I'm just going to pick one for time. It's regarding to the fast process bio oil. There you are. The question is whether this fuel would allow the SmartCHP system to be used in city centres which have strict clean air requirements.
Well, one reason is, of course, that we have a flue gas treatment here, and it depends also on local regulation and so on. But we have a flue gas treatment that we will be well below any emission limits set. And when we compare, for instance, to a biomass pellet burners, and that might also be an issue in city centres, we are much lower. But on purpose, there's a reason to have a flue gas treatment in the system included.
Okay, very good. Due to time, we're going to move on, but yeah, like I said previously, we'll come back with some more questions in the discussion. So thank you very much, Bert. And the next presenter, I think I'd better introduce myself, because it is Giulio from project manager at the EU Biomass Industry Association, and he's going to present a little bit about our BIOCOGEN 2030 stakeholder platform. So
thank you, James.
Giulio, all yours.
So, do you see my screen?
We see your screen. We don't see you. Yeah, there you are.
There we go. Okay, so I just start the presentation. Okay, so as I anticipated at the very beginning, I'm gonna talk about BIOCOGEN 2030, which is the joint initiative launched by the projects Blaze and SmartCHP quite recently, after we came out with the press release a couple of months ago. So BIOCOGEN is a stakeholder platform that we launched, and it aims to gather stakeholders active in the field of biomass cogeneration. It wants to facilitate the sharing of knowledge among the members, share good practices and experiences. It wants to be a kind of speak out tool in order to promote innovative, curious, interesting new solutions in the field of biomass cogeneration, and wants also to be a debate forum for our members. It's open to everybody, basically companies, universities, research bodies, and associations with interest in this field. And we wanted to keep very informal and easy, since the registration, you can fill a Google form and you are registering the platform. So you can actually find the registration link in the original webinar page, and of course we will share it again after the presentation. Then we our focus areas, the areas that the topics we will discuss, we will treat in our activities will be mainly four, and there will be biomass characterization and suitability, process developments, market assessment, standardization issues, and the discussion on non-technological barrier, and finding solutions on how to overcome them. How we are gonna achieve our goals, our aims. So we've started to set up dedicated pages for BIOCOGEN 2030 on the websites of Blaze and SmartCHP projects. From there, you will see news on the upcoming activities, on the upcoming webinars, or information. We are in the process of setting up a LinkedIn page, but especially a private group on LinkedIn, so we can facilitate the networking, the encounter of the meeting of our stakeholders, and sharing of knowledge that I was describing before. Obviously, a newsletter will come with the registration. Not going to be an annoying newsletter. It's going to be a monthly or bi-monthly newsletter. We also would like to circulate surveys on specific topics regarding cogeneration from biomass, from which since it's a very open and flexible environment by BioCOGEN, we also encourage you to submit your proposition, your suggestions, so that it's a really participated forum and environment. Then we'll try to hold regular webinars. Initially, we hope to have also stakeholder workshops in person, but as you can imagine, now it's not the right moment. And coming to what we were planning to do for the rest of the year, for 2020. So today is the launch webinar of BioCOGEN, following the press release last month. In the coming months, we will try to work as a dissemination tool, as having this speak out function. So we would really like to have more stakeholders joining, and we would like to promote and give room to new projects, new ideas, or even companies with very interesting solution regarding cogeneration from biomass. We would like them to come forward, and we would like to help them in spreading their solution and innovation. As I said before, we wanted to organize a stakeholder workshop in person in Brussels in October. Obviously, this is a fictional date because we won't know if in October we'll be able to actually organize it due to the COVID-19 emergency. But for the time being, we are going to be present at the European Biomass Conference and Exhibition, because as you know, the EUBIA, organization I'm working for, is one of the co-organizers of the European Biomass Conference and Exhibition, which was due to take place in Marseille back in April, but of course has been postponed, and it will be all this year entirely online, using a special software designed for virtual conferences. So in this virtual environment, EUBIA will have an exhibition area, which will have a dedicated section to BioCOGEN 2030, where we will find all the useful links and information. And in this framework, we would like to have a speak-out session. What would we mean by speak-out session? We would like to have a webinar like today, where we give the chance to other projects or companies with interesting proposition in the field of cogeneration from biomass. We would like to give them the chance to speak to the conference and exhibition audience, and to attract newcomers to our platform, so that we can grow all together. This webinar speaker session will take place on the 7th of July. We are still working on the time slot, but it's going to be most likely in late morning. It's going to use probably Zoom, and as I said, it will give the opportunity to present promising projects in the field of cogeneration from biomass and extend the BioCOGEN 2030 network. So pretty much everything from my side. So to wrap up, BioCOGEN 2030 is still in infancy. It has just started its path. It's an open forum that also would like you to come forward and help us shape it. And what can BioCOGEN do for you? BioCOGEN can grant an informal and flexible forum helps you to create synergies between the various stakeholders and projects coming forward. It will allow you to enlarge your network and also help with the dissemination of your project and activities. So I can only say register to BioCOGEN. We will circulate all the crucial link after the webinar in a follow-up email. And I thank you for the attention as well as all the other speakers.
Thank you so much, Giulio. That's excellent. So I think we can move on from there straight to the panel discussion. So I would like to invite all of the speakers to put on their webcam and to join us. And I will pick out some questions here. So Hans, are you still there?
Yeah.
Perfect. Very good. Well, the first question is directed to you. Maybe slightly outside of your remit, but we'll see what you have to say. So we have quite an international audience. So there were some questions about cogeneration worldwide. About what would you see as the hotspots for cogeneration usage, and especially if you have any information about Southeast Asia and the use of cogeneration systems.
That's a little bit out of my remit. I actually know a little bit more about what's happening in the United States, Central America, and South America. There's actually, I would say, a growth in that segment there. And I think one of the things that is fueling CHP in those markets is the relatively cheap shale gas coming from the United States, which makes the spark spread very interesting in those countries. So those countries are investing significantly in CHP for industrial processes on that side of the world. CHP, I know more about what's happening, for instance, in South Korea and Japan. They're actually, at least in Japan, fuel cell micro CHP is a technology for homes and small businesses, has certainly taken off, and Europe is looking to actually Japan in terms of how they best done it in terms of scaling up that technology in those markets. Southeast Asia, I'm afraid I don't know too much about, but I'm sure there is potential.
Thank you so much. Yeah, I was fishing a little bit. I mean, the clue is in the name COGEN Europe that we shouldn't be asking too many questions of international ones. But hey, we have an international audience, so I thought we can try. So for Enrico, a question: if you could give some more details on the gasifier that you're using in the Blaze project.
Yes, I will try to speak slowly now this time. Okay, no, maybe. Okay, so the gasifier, okay, is an interesting thing from a general point of view because you have directly a gas. So what you use is only a gas, not burn a solid or a liquid. You have what's only burn is a gas. So the gas can be well converted than the solid or liquid. And if you have a solid or liquid, you have to always go to the gas in order to use. So it's interesting, okay, but it's also interesting the things to have hydrothermal cracking or have pyrolysis for very different type of biomass because it's difficult to transform a solid from a gas. Okay, so this meaning that in a single reactor, okay. And so we try to use the technology is a fluidized bed. This meaning that there is oxidizing agent that is also a fluidizing agent. That meaning that taking suspension the solid, so the solid is becoming a liquid. Okay, it's the same property of a liquid. Okay, in particular, this is a bubbling because the minimum fluidization velocity is the fluidization velocity is similar to the minimum fluidization. It means that it makes a bubble, like the bubble, okay, no, in the boiling of water. Okay, so it's a bubbling flexible gasifier. We choose this technology because it's more compact regarding for the small, medium scale. Okay, if you have no, a larger scale, of course, it will not be needed. Okay, so we try to use a bubbling flash-bed gasifier. Also, and it's undirected. This meaning that the heat for the gasification is coming from another reactor. Okay, that burn the char unreacted. Okay, and give changing the material that is hot, more hot in the combustion reactor. He give the heat for the gasification. This type of technology, the fusion, is made 40 years ago in the United States and in Boston. Okay, we have one professor that is with the dynamics. Okay, with the professor in Boston from the University of L'Aquila. Okay, normally they made 2 fluidized bed. Okay, circulated fluidized bed. We try to patent use a 2 bubbling fluidized bed. Okay, maybe this is too much for describing the gasifier. Okay, this meaning only that it's a fluidized bed. This meaning that all the temperatures are equal. Okay, there is an instantaneous conversion of the little piece of biomass because there is an inertia over the fluidization material that is very hot. When you put a little piece of biomass instantaneous, it's become pyrolyzed, not drying, pyrolyzing. It's a phenomenon that becomes instantaneous. In this way, you control the temperature and pressure in each part of the reactor. There is not a spot like the fixed bed. So it's a little bit more complicated in order to design, manage. From a realization point of view, it's more easy that the fixed bed. You don't have the bed. Okay, you don't. So it's also more easy to. So okay, I don't know. It's a particular bed for a gasifier. It's patented and so on. But there is also in the industrial area a lot of fluidized, bubbling fluidized bed. Okay, circulated. No, okay. So this is we try to do that in order to have come to decrease the size. Okay, because normally the type of fluidization is applied to megawatt scale reactor. Instead, as SmartCHP, we want to go to the small to medium scale, and so we try to use the fluidization technology for also 100 kilowatt of size. Okay, so we already use this type of gasifier in the Unique project, in the Unify project. So it's more than 15 years that we work on this technology. We think that it's a good idea in order to have a very good gasifier at small size, compact, and so on. Okay. Of course, we have a problem when we have biomass with high ash content, more than 20%, and for the also with melting point of the ashes that it's lower than our temperature. We can control our temperature, but in order to gasify, you have to have at least at 800 Celsius degree. Okay. So this meaning that if you have a melting point at 700, 600 Celsius degree, it will be a problem for the reactor. And so it's good, but okay, up to now we cannot go. We tested. You cannot use for any kind of biomass. Okay, for the lignocellulosic monomass, it's very good, and we have a very good results. But you can see in the website of Blaze, you can see the rest of the biomass selection and the preliminary also gasification test, and so you can check a little bit better. If you go in the search in the website Unify project, you see also when we invented this kind of gasifier, there is a better description of gasification. Okay, and the type of gasification. So I hope that okay. I explained. Okay.
Perfect. Thank you very much, Enrico. A question for Bert, related to the conversion of the diesel engine. How efficient is this conversion process economically and technically, and what is the constraints with developing this new fast pyrolysis oil based engine?
Well, the basis of the engine is a standard diesel engine, and the majority remains completely the same. The big advantage of using a standard engine is that due to mass production, they are relatively cheap. The only change we are doing, or it's mainly related to the fuel pump and fuel injector, because it's acidic and you need something which is corrosion resistant. And so in fact, what we actually change on the engine is fairly limited. And of course there are some other changes, but it's not really a complete new engine. It's really a small, it's a modification to an engine to be able to fuel this pyrolysis oil. If you look from a techno-economic point of view, I think for combined heat power in general, but certainly for smart CHP, and probably it also holds for gas CHP, the majority of the cost is the fuel and not the investment or the depreciation. Of course, there is some maintenance. Maintenance is important here. We should avoid excessive maintenance. But I think for this kind of systems, the main part is not on the investment side of the engine. Yep.
Okay. Well, I think that brings on to another question, which I think can be addressed to yourself, Bert, but also Enrico, and also probably Giulio, to talk more about the feedstocks themselves. So which feedstocks are both projects sort of targeting, or are them, let's say, the most suitable for the two technologies? And then also, what sort of details do you have about availability of these different feedstocks and the future prospects for that?
Yeah, maybe I can answer first then. Within Smart CHP, a lot of development will be based on wood-based pyrolysis oil, because simply it's available. We have the Empiro plant nearby. They have huge amounts of pyrolysis oil, so for the development that makes it easy. But at the same time, we're looking at other types of feedstock. And actually, there is a deliverable just completed on biomass availability and selection for different countries in Europe. And if I remember well, we will at least do also the olive kernels, corn stovers, and also forest residue. I'm not 100% sure if I had the right selection, but they also looked at availability throughout Europe. It should be sufficient to feed a single pyrolysis plant, which is roughly 40,000 tons a year. The pricing of the material, the alternative use, and so on. And so we just completed a report on biomass selection, and I think it will be public, this report. So there is some activity ongoing there. If you look at pyrolysis, of course, wood is an ideal feedstock. Also, if you look at sawdust, that kind of things, because there are limited contaminants, there is no minerals, although in the oil itself the minerals are always low, but there will also be some transfer of inorganic material to the oil. That's what you would like to avoid. But we will in the project we will look at different of pyrolysis oil derived from different biomass feedstocks, but the majority of the development will be based on wood. Yeah.
Can add some point. Okay, I completely agree. Okay, but I would like to add maybe a little bit some more detail. Okay, first, okay, for us, for example, of course, for all the type of biomass, the woody biomass is good because it have a good calorific value, normally low ashes, okay, low contaminant. Okay, and for example, for us, for the flat bed is good the nut shell, almond shell, and so on. Okay, because are dry, no less than also 15% of humidity, are already little. Okay, for flat bed is good. Okay, you don't have also crash. Okay, and so on. So we start also for all the type of nut. Okay, nut shell, all the type of shell, nut shell, almond shell, and so on. Okay, of course we use also pruning of waste or pruning of a lot of wood, and this is also good normally. Okay, in general we want to use as already told all the type of biomass waste. We have to understand that the most important are the primary agricultural residue. Okay, that is very large part. Okay, and there is also the residue from forestry. Okay, and there's residue also from municipal waste and industry. Okay, all these about 600 of megatons per year that are in Europe that can, okay, represent an energy that is almost half of all the fuel for all type of transport that used in Europe. Okay, they can produce almost all the electricity energy in Europe. Or if we can allow to use all this type of waste biomass. Okay, but this is a little bit difficult. So if in our project, if we start from the left, there is the more easy. If you go to the right, okay, there is a more difficult that we have. Okay, so we use also some waste from timber food distillation. For example, if you think about the black liquor from the still now in Italy there is not too much, but in the part of Europe you start to have black liquor because if you use wood to make paper, okay, you have a production of black liquor, and it's also a little bit difficult to use for the ashes content. There is also other and so, but you can check, you can fix some problematic and use. And after we have a very on the right, we have the very difficult that still we not arrive to gasify properly. This is organic fraction multi-soil waste and the digestate. Okay, still we have a little bit of problem on that. If you go on the website of Blaze, you find the Derivo 2.1, and you find that it's connected with a European project that is AS, you find in 2 biome, okay, and there is all the potential in all Europe, in all region of Europe, so it's per country and per region per country, in all the type of biomass availability. And we use this kind of potential, and we take a representative for each category, and we make analysis of the biomass, so preliminary and definitive analysis, and we make also analysis of the ashes, melting point of the ashes, and so on. And this is the report you find 50, 100, no, it's 70 page of report in the website of Blaze. Okay. And so it's true that a very good important point is try to use the dirty biomass, the high humidity, high catch content, high sulfur chlorine content biomass. This is a very problematic point that has to be solved in next year if you want to increase the biomass use. Okay. Thank you.
Okay. Thank you very much. A couple of questions directed to you, Bert, about your fast pyrolysis bio oil. The first one, if you're using the bio oil within SmartCHP without any additives like alcohols or other mixtures. And then the second part to the question, if you have any price estimations for fast pyrolysis bio oil or any comparisons to pricing for wood chips, wood pellets, diesel oil alternatives. I don't know if you have your microphone on, Bert.
Sorry.
That's fine.
To start with the first one, do we add anything to the oil? In principle, we use just crude pyrolysis oil, but to simplify testing, we very often use pyrolysis oil in combination with about 10 or 28% of ethanol. In principle, we can run without, but by adding some alcohol, the homogeneity increases and it reduces the viscosity. And so a lot of testing we are doing with 28% alcohol added. For the pricing of pyrolysis oil, you should ask my colleagues from BGG, BGL, and they know better, but I think we published some data on it, on the pricing of the Imperial demonstration plant. And I think the data which was published is somewhere around 300 euros per ton. So that's public data. Yeah.
Okay. Thank you so much. Yeah, now I have a big question, which I think is open for everybody to give their views on. Question about what do you think are the most crucial aspects to achieve the large diffusion of CHP technologies based on biomass? So what's really going to be the key to the wider uptake of these kind of technologies? So the questioner sort of suggests, is it feedstock availability? Is it the technology, the public acceptance, incentives and costs? Very open anyway, but I'm sure you will have your own opinion. So maybe Hans has some thoughts on that.
Well, will maybe focus my answer more generally, looking at all CHP, which also applies to obviously biomass. I think we are at a crossroads now in Europe in terms of EU legislation that will develop and create the markets of the future. We're looking now at the European Green Deal, which will take us to 2050, but also in the medium term to 2030. So we need to have the right infrastructure in place in terms of EU legislation to ensure that the qualities of CHP and including biomass CHP are recognized in EU legislation, such as the Energy Efficiency Directive, which is going to be reviewed in the context of 2030. And so energy efficiency, the energy efficiency principle, the notion of focusing on primary energy savings, not just final energy savings, these are all important things that need to be recognized and enshrined in EU legislation. So Article 7 of the EED, Article 15, Article 14, these are all important pieces of legislation that will help recognize and allow member states as well as regions and local communities to utilize CHP towards those EU energy and environment objectives generally.
Yeah, very good. Enrico, you're waving.
I will also add some point. Okay, so for example, no, the problem I think of cogeneration is maybe you have an high investment. Okay, because it's low investment if you have a boiler, if you have a electricity, only electricity generation. Okay, so you have a high investment. So if you can use low cost fuel, okay, this helps. Okay, because at the end in the power plant, what is most important cost is the fuel cost that you have. Okay, apart from some solar plant or something like that, of course. And so in this case of cogeneration, it's very important, for example, biomass, because when you have biomass, you have always straight with heat, so you have heat, and very good to put also cogeneration. Okay, transforming natural gas, yes, it's very easy to have a cogeneration because the natural gas is very, but from a general global point of view, okay, it's not so intelligent to use a gases, okay, forever heat. Okay, no, it's meant to use for other solution. Okay, so I think that the change, so the step forward in the cogeneration, it will be to understand that and to really find a way to have to know the molecule, okay, to of the complex substance that are related with the heat production, like biomass, for example, and so to have a really efficient low emission system. In this way, okay, it's in the building, okay, each on so you have so you put banana waste in your boiler, but now you have maybe an electric boiler or a gas natural boiler. In the future, you will have a gasifier with soft, for example. You have a cogeneration in your house, or you have industrial cogeneration mega size. Okay, but to do that, you have really make a step forward in the understanding of the complex molecular that are from solid, okay, that can transform. Okay, so here, in order to use a very different type of waste in a very efficient and a very zero emission system. We are not at this stage now, okay? So we have a little bit, we are increasing, we are better improving, but still we are not solved the problem. So, but so this I think will be the step very back to in the cogeneration, okay? Using the fuel that it's made for heat, okay? And also producing electricity with a very high efficiency and low emission. And so all the possibility here, we have a lot of possibility, and when we develop really well this technology, will be adequate. Okay, thank you.
Thank you. Maybe Bert, do you have any thoughts on that topic?
Well, maybe I can add a few things. That's maybe from a technology point of view. In particular for this kind of system, if we want to implement it, we need to robust technologies, and anyhow they should be cost effective. Only sustainable is not enough to get it implemented. And if you look at small scale, I think there should be the possibility for a high level of automation, or at least it should be unattended operation. You cannot make it cost effective if it needs continuous attention. So it should be fully automated, unattended operation, robust, limited issues. For the pyrolysis-based system, of course, it's also important to have access to the pyrolysis oil, because that's the fuel. And that's what we see now. The technology is now implemented in Europe, it's getting mature, the product becomes available, but that's also an important boundary condition if you want to implement a SmartCHP system. And but that's now going on. As mentioned, I estimate from next year onwards, in Europe, there will be 100 million liters produced every year. So there is some fuel available. And I think a single SmartCHP might need a few 100,000 liters a year. So it's getting into the market. But I think in the end, it should be a robust technology and in particular cost effective.
Yep. Excellent. I think we're about round really in terms of time. So Giulio, I don't know if you wanted to just say a few concluding words.
Yeah, I would like to thank all the speakers for their very interesting presentation and for their ability in answering the questions coming from the audience. Just to concluding words, we will circulate a follow-up email, including all the presentations, the various links, the recording of the webinar, and of the news relative to the upcoming activities of BioCOGEN 2030, which again I encourage you to subscribe. Then you can follow the developments of Blaze and SmartCHP here on LinkedIn or on Twitter. And then stay tuned, and looking forward to see you at the next webinar at the UBC 2020.
Very good. So I think with that we can conclude. So yeah, thanks again to all the speakers. Sorry, Giulio.
What?
You wanted to add something? No? Okay, sorry. Well, I think you wanted to say something.
No, I only want to thank you to all. Okay, very thank you all. I think that we can make a good work, and we can make a link also with SmartCHP. We have a lot of similar activity. I would like also to ask all the people that are participant here to suggest if they are working in a similar sector to give us to join with a network, put together information and so on, in order to more share our activity, our deliverable, our work. Okay, it's better for the knowledge and the sector. Okay, so for me it's a really interesting meeting. I thank you all. Okay, thank you.
Okay, so we end the webinar here. Thanks all very much for joining and participating, and we look forward to seeing you at future events. So thank you all. Bye-bye.
Thank you. Bye-bye.
Bye-bye.